Hi everybody, thanks for coming along and thanks for staying. My name's Sam Burns. I'm a developer, software architect and application security researcher. There's a copy of the slides on the website at the bottom if you'd like a copy of them. You can get in touch with me on the social media links. I'm not very chatty, but if you have questions about the talk, I'm sure you'll be able to find me. Now, what I'd like to talk about today is the new weak package that's been added to Go. This has been added to Go 124. I'm going to do an overview of what weak pointers are. We'll talk about garbage collector in Go in a little bit more detail and what happens on bin day. There'll be little comparison to other languages. There are other languages that have features similar to the weak package. We'll talk a little bit about those. I'm going to go through an example use case of what you can use weak pointers for in Go 124. There'll be an example involving caching, and we'll talk about some best practices. Now, first of all, this is what happens if you try to explain the concept of a gopher to mid-journey, by the way. First of all, a guide to the new weak pointers feature. So let's take a look at Go's new weak package. So this is a new feature added in Go 124, which was released in February, I think, sometime around Valentine's Day, mid-February. So thanks very much to the core Go team for that. These are special references which don't prevent garbage collection. They're non-owning pointers to an object. When I say object, I don't mean in the sense of object orientation, just a thing that's in memory, a Go variable. They allow for the object to be collected by the garbage collector when otherwise unreferenced. And we'll be looking at what you can use this for and some of the details of the implementation in Go. So, first of all, why weak pointers? What was the point? And why, after many years of discussing it, did they eventually decide this was to be added to the language? Weak pointers allow you to create caches which avoid memory bloat problems. They can avoid unnecessary retention of objects. We'll go over some examples at the end, not just in terms of caching, but also things like observer patterns and other times when you might want to be able to refer to an item that's in memory without preventing it from being garbage collected, and to enable automatic cleanup in long-running programs. There are other applications as well, canonicalisation maps and other things, which we'll discuss if there's any time at the end. Now, the conceptual overview. Weak pointers don't count as far as the garbage collector is concerned in terms of reachability. They can return null once an object's been collected. We'll discuss that more in a little detail in a moment. And this is in contrast with sort of normal pointers. I'm going to call them strong pointers for the purpose of the talk, but I mean just pointers. You know what a pointer is. Ones that aren't weak. So if we have a look at a diagram, I'm afraid this wasn't mid-journey, this is just me. But if you take a look at a diagram representing an object in memory and Go, a strong pointer is just a reference to it. A weak pointer kind of counts as a reference to it as well. So if we think about what's going to happen if the strong pointer goes out of scope, and if the object that it's pointing to also goes out of scope, then all that's left is the weak pointer. So what happens to our object in memory the next time the garbage collector runs? I'd like to thank Juan de la Cruz Garcia for the one piece of artwork in the slides that is actually good. So when the garbage collector comes along, this one wasn't me. When the garbage collector comes along, the object that's in memory gets removed, as you can see, quite dramatically. So, how do they work in Go? Well, they've added a new package into the standard library called the week package. You can use generic types, so week.pointer is a pointer to anything whatsoever, really. And it's created with what I'm referring to as a strong pointer. So it's created with a reference to a variable. So in this case, we've got a variable which is called object. We've created a reference to it, and then week.make in the new standard library function is how you're creating this week pointer. So to take a look at what that might look like in a code example, if we look at this code here, first thing it's doing is creating a variable, then a pointer, a regular strong pointer over here on line 11, which is a pointer to this variable. And then we can use the new week packages week.make to create a week pointer based on the strong pointer. So you can see there on line 12, this is being created not from the object that's in memory, but from a pointer to it. Now, before the garbage collectors run, the object's still strongly referenced, basically meaning that this pointer variable declared on line 11 still exists. So there's a strong reference to it. Also, the garbage collector hasn't run yet. So what we'll see here in this if statement is that when we get the week pointer and convert it to a value, the value is a normal strong pointer, a real pointer. If, however, we artificially remove the weak reference, if we artificially remove the strong reference and then run the garbage collector, then something else happens. Now, you don't need to run the garbage collector manually very often in Go. There's usually not a good reason to do it. You can do this if you want to, but it's largely for demonstration purposes. We can talk more about how it happens automatically and under what circumstances and how you can configure it. But for demonstration purposes, I've run the garbage collector manually, which you wouldn't expect to see very often. And now there's no longer a strong pointer to a variable anymore. So what happens is when you call week pointer, it actually prints that the garbage has been collected, or the value was collected. So we've tried to resolve the weak pointer after the item it's pointing to is no longer in memory, and it's returned none. So what this means is weak pointers return nil when the object is collected, or when the object has been collected. So there's no risk of dangling pointers. It can't return you a pointer that doesn't work anymore, a reference to invalid memory. It'll return nil, but that does mean you have to check whether or not it's returned nil before you can actually use it. So when you're using weak pointers safely, kind of every time you call wp.value, even if it's worked before, it's still worth checking whether or not it's returned nil. Now, to talk more about what happens in Go's garbage collection, or what happens on bin day, a guide to garbage collection in Go. The garbage collector is tracing mark and sweep garbage collector. That means it's essentially going through memory and working out which objects in memory are still being used and which aren't, and then the sweep phase just means deleting stuff that's not being used anymore. The strong references keep objects alive. If there aren't any of those, then that means that an object in memory is eligible for collection. So in terms of the way the memory allocation works, a stack is local variables for a function or a Go routine. But the heap, if you were to create a global variable in Go, or a package level variable, then it would go in the heap. Objects in the stack may be pointers to the heap. What that means is you can have a global variable that's passed into your function or your Go routine so that a reference to it exists in the stack, is still being used, but the object, because it's global, lives in the heap. So the way Go's garbage collector works normally, it's called a tricolor mark and sweep garbage collection. This is operating over the heap, not the stack. And what it's essentially doing is marking items in memory in 3 colours. So in this example over here, we've got a root node which represents an object in memory that's represents an item that's, for example, a global variable that's pointed to by something that's in a stack for one of your functions or one of your Go routines. I've been referring to them as objects, but it could be that it's a simple variable. It could be a struct or a backing array for a slice, for example. Once it's been identified what the root nodes actually are, such as this little star down here, they then get marked. Other objects in memory get marked in 3 colours, so they all start off as white. Basically, by the end of the process, if something's still white, that means it's going to get deleted. So the way the tricolour mark and sweep works is the child of any element which is still being used or can't safely be collected gets marked in grey initially. Grey means it's still reachable by userland code, but that it may have children which haven't been scanned yet. Black means definitely still needed and doesn't have any children that haven't been scanned yet. And white means we haven't found a way of reaching it from userland code. So if you imagine, for example, you've got a global variable which is referred to by one of your functions, so it's been identified as a root node. It might, for example, be a struct, which means it'll have several properties, each of those. So the initial struct gets marked as grey, meaning it's got children that haven't been analysed yet, but we know we can't delete it. And eventually everything that's in the heap gets labelled either in black or in white, depending on whether it's reachable from userland code or not. At the end, the white bits here are the parts where that variable's no longer used, it's unreachable, and it's safe for the garbage collector to remove it. Now, a lot of the garbage collection in Go is happening somewhat concurrently. The sweeping, for example, can happen when your code is running. If we've already identified the white bits, there's no way that your code can possibly be using them, then freeing up that memory can happen concurrently while your code is running, because it's already been exhaustively proven that your code doesn't depend on these bits. So there's no reason why the sweeping can't be done concurrently with the rest of your code. There is a brief stop the world when it comes to identifying root objects. It's difficult to benchmark, sometimes takes about 100 microseconds, doesn't really increase with the amount of memory that's been allocated. Fortunately, it can take a little longer if you have a very large number of Go routines running, but it's not that intrusive in terms of performance. And while the marking is taking place, there's also a kind of concurrent write blocking where the tricolour marking is being redone whenever you try to write to a variable. So you can read to variables while the marking, you can read from variables while the marking is happening. If you write to a variable, that bit can be slower if the garbage collector is halfway through doing the marking, because it needs to work out the implications of what you're doing on its marking. So the write blocking means, well, perhaps blocking isn't the right word, but it does have a slight impact on the performance of writing to memory while the garbage collector marking is in progress. And there's a brief stop the world pause at the end as well as part of the tidy up. But overall, Go's garbage collection's quite a quick one. Comparing it to other languages, it's a tricolour mark and sweep. I'm particularly proud of this bit of Clipper. It's a tricolour mark and sweep garbage collection. Stops the world when necessary, often concurrent. It's a non-compacting garbage collector, so in some languages, including I think most implementations of JavaScript, when garbage collection is taking place, if you imagine a large amount of memory and bits of it have been identified as not being used anymore and are unallocated, compacting garbage collector squashes everything together, meaning moving items in memory so that they're contiguous, so that they're all in a row. That means that it's a little slower. If you use a compacting garbage collector, it would also mean that if you had pointers, they would need to be changed on the fly. In use land code, the actual value assigned to a pointer would need to be changed. Go doesn't do that, but it's quite good at keeping track of where the gaps are in memory that's been freed up and working out what can fit where when new memory is being allocated. So it avoids the slowdown associated with compacted garbage collection, but it's quite efficient at reusing the memory anyway. It's a non-generational garbage collector as well. There are other languages, I think, don't quote me on this, but think PHP, for example, where not every variable gets inspected every time the garbage collector runs, and there's a general assumption that if an item in memory has been there for a long time and survived many rounds of garbage collection, it's less likely to be removed in the next steps. So sometimes things get skipped to save time. Doesn't happen in Go. So it's a non-generational, non-compacting garbage collector. You can configure it with GoGC, which is an environment variable you can use. There have been some cases of people making I think Uber are saying that they've made a system that actually profiles their services and configures the garbage collector according to the needs of the individual service. Our hosts have published a fascinating blog on benchmarking some sort of cryptography or hashing protocol in Go, where it was found that turning the garbage collector off entirely increased the speed of their program without impacting the memory adversely in one particular use case. But in general, you don't really need to change it very often, but you can change this if you want to. So obviously the benefits of Go having a garbage collector, well, it's easier for the developer. There have been studies on CVs on cryptographic libraries written in C that suggests that as many as 25% of security vulnerabilities were memory management issues, which isn't as much of an issue with Go. So we've got a lovely garbage collector and we should be very happy with it, is what I'm saying. Now, regarding the weak pointers and reachability, strong references keep the object alive. Weak references are effectively invisible to the garbage collector, and a weak reference can be nullified if the thing it's pointing to gets collected. So it's as if we were able to have an indirect reference. Okay. Now, preventing early garbage collection, you can do this if you want to using runtime.keepalive. If you find yourself doing this in conjunction with weak pointers, it might be worth just double checking if weak pointers are definitely a good fit for your use case if you're also trying to suppress garbage collection manually as well. But it can be done if you want to. This runtime keep alive package function has more uses in other areas. I think one of the more old-fashioned ways of interacting with Go's file handles required you to use it sometimes, and if you're using CGO, for example, it can be necessary to keep something in memory because it's very difficult for Go's garbage collector to tell that it's still being used in C. But that's perhaps a subject for another talk, which I'll be doing soon. Language comparison. So to take a look at how this works in other languages is very similar. I think there was a lot of discussion over the years as to whether or not to add weak pointers to Go, and I think one of the arguments that was put forward both for and against adding it was that it would make it more like Java. So Java has this this feature here, java.lang.ref.weak references, which does what you'd think it would do. You can use get to get the object. I think it retrieves the actual object itself, not a pointer, because it's Java. And it can return null if the object's been collected. Has the same underlying principles of non-ownership. And another language which does something similar, C#, where you can use system.Quick reference and try get target is a thing that tries to get the target, one can only assume. But this is again a case of trying to resolve the weak pointer if it's possible to do so. Excuse me. Now, in terms of a practical example, we can take a look at how you might be able to use weak pointers to build a cache. So the use case here is cache entries shouldn't prevent collection, object collection. Weak pointers lets the garbage collector reclaim unused cache items, and you need to check for nil on lookup. So what I mean by that is, if you imagine you've got a cache and go, this is a map, and we've got string keys here, which are called key 1, key 2, key 3. Each of those points to a weak pointer. It's possible to get a cache hit saying, yes, key 1 is in the cache, and there's a weak pointer in it which points to a picture of a gopher. An object that's in memory. There's also obviously it's possible to get a cache miss if the cache key isn't there at all. There's a third case here as well, which is if the string that you're looking for, the cache key, is found in the cache, but the weak pointer that's in the cache is no longer there, then this is a kind of third case of a cache miss, but it appears to be in the cache when you check. So what we need to do in our caching code is, first of all, check, is the thing in the cache? And secondly, has the weak pointer been nilled, in which case we should delete it from the cache. So to take a look at what that might look like in terms of code, what we've done here is created a cache which I've used this map here, which is a map to weak pointers of, we've decided to use integers here. On line 10 and 11 we create some data in a cache key. What's actually getting cached on line 12 is a pointer to some data. And then, so when you're inserting an item into the cache, you insert a weak pointer. If you would like to do a lookup, then sort of implied here, we haven't really handled it, but it's possible for there to be a complete cache miss, or it's possible that there's a cache hit on the key, meaning that the key is in the cache, but we still need to remember to check every time you resolve a weak pointer, find out whether or not you actually got an element. If you did, then you can return that as a normal cache hit. If not, then it's implied here that we're tidying that up by deleting the cache key as the pointer's now expired. So to reinforce why this approach solves a problem with caching, the cache itself doesn't prevent garbage collection. It allows for memory efficient caching without manual eviction. There's a little bit of a trade-off. We've got some simpler logic than manual eviction, where we're checking if the weak pointer has been invalidated and reloading the cache entry if it's nil. But other than that, what we've been able to do is to create a cache where essentially the memory can be reclaimed. Now, best practices for using weak pointers. How are we doing? Have I got time? Yes, okay. A few best practices. First of all, obviously checking for nil. verifying every time you use weak pointer.value to avoid nil pointer dereferences. Another thing is concurrency considerations. The weak package itself is thread safe. If we look back at some of the code that was written, the map feature isn't, and sync.map, for example, in the Go standard library would have made this thread safe, but the underlying weak pointers are perfectly thread safe, so there's no concerns there. So they're perfectly safe for concurrent reads. So in summary, we're about done, but there's a couple of other uses of weak pointers. Event listeners are observers that don't block cleanup of their subjects, as an example. So you might be able to imagine wanting to have something like a pub sub like a pub sub pattern or an observer pattern, for example, where a listener is essentially able to monitor an object that's in memory, but without stopping it from being garbage collected when it's not being used anymore. So this would allow you to have an observer which is not preventing cleanup of the thing that it's observing. There are other benefits, caching large computer data. There's a data structure called a canonicalisation map, for example, also known as interning, where this might be useful. And so in summary, the new weak package, weak pointers, non-owning references that don't block garbage collection. Always remember to check for nil and manage lifetimes carefully, and they're useful in particular for caches, canonicalisation maps and observers like we've talked about. Thank you.